Hello and welcome to another Sussex Universe lecture. In fact, welcome to the first Sussex Universe lecture of the new academic year. For tonight's lecture we have Dr. Roger Luther. Roger was actually one of my lecturers when I did my degree, and I can safely say he was one of my favourite, and I probably owe quite a lot to him for being where I am now as a PhD student. But regardless, tonight Roger is going to be talking to us about Euler's amazing constant, and without further ado I will hand over to Roger.
So I'm going to talk this evening about something called the Harmonic Series and Gamma. My name is Roger Luther, I should have said. I'm a teaching fellow here at Sussex in the maths department. I've been here about 19 years now. And normally each year I do a talk like this to the Sussex University Maths Society, SUMS. But this year that didn't happen, of course, back in April. So this, in a sense, is what I would have done. Now, the harmonic series is a very simple series to define. It's just the sum of all the successive reciprocals of the natural numbers. And you can look at it from a finite perspective, the sum from 1 up to 1 over n, but we'll also be interested in what happens if you go on forever, as what happens as n tends to infinity. And this was first discussed, as far as we know, by one of my mathematical heroes. Very few people have ever heard of him, Nicolas or Nicole Oresme. I don't even know how you say it, Oresme. He was a French, what's the word? Well, polymath. He was the Bishop of Paris. He was an economist, philosopher, mathematician. In those days, you did everything. If you had a brain, you weren't so specialised as we are now. And this was a very dark period for mathematics. Not much had happened really since, I suppose, I don't know, well, since the Greeks maybe, in terms of new mathematics. It was almost the Dark Ages. But in the middle of that, Oresme had one or two insights which we can now recognise as being very clever. He, for example, probably had the first idea of x and y axes on a graph, but it didn't catch on until 300 years later with Descartes giving us Cartesian coordinates. Oresme had the idea of using rational numbers for indices, so 3 to the power of a half, meaning the square root of 3. But what I want to look at is the proof that he gave for the fact that the harmonic series actually diverges. It goes off to infinity. Even though the numbers you're adding get smaller and smaller and smaller as you go on, it's very easy to show that you still end up going to infinity. And the proof is something like this. We simply replace each number, or we group the numbers together in, first of all, in a pair, third and a quarter, and then 4 of them, and then there'll be 8. And within each bracket, every number is at least equal to the number at the right-hand end of the bracket. So a third plus a quarter is at least as big as a quarter plus a quarter. And the fifth, sixth, etc., up to an eighth is at least as big as an eighth plus an eighth. But once you do that, you can see that these brackets just come to a half, 2 quarters, 4 eighths, 8 sixteenths. And so what this is showing is that you can always get a bunch of numbers together in a long enough bracket that will give you another half to your total. And so there's no limit, because we've got an infinite source of these reciprocals. We can go as far as we like to the right. We can always find another batch that will give us something at least equal to a half. And so the series diverges because you can keep adding on halves as long as you like. So that's one answer. It does diverge, but a sort of related aspect of it is that it diverges very, very slowly. The first 100 terms only come to 5.18. The first 1,000 only come to 7.49. the first million only come to 14.39. And it's quite easy to see that it's going to take a long time to get anywhere. And one simple result is that once you've got to a certain total, by using up to 1 over n, if you double the length of the series, you will add on less than 1 to your total. So if the first n terms add up to k, then the first 2n won't take you to k plus 1. And that's easy to see because if we've got the first n terms, the next n terms are 1 over n plus 1, 1 over n plus 2, etc., up to 1 over 2n. And each of those is less than 1 over n. And there are n of those, so they add up to 1. So our total of the n plus 1th to the 2nth term adds up to less than 1. In fact, it's quite easy to show that you need approximately e times as many terms, so about 2.7 times as many terms to add on 1 more to the total. Now let's try and get a more precise handle on hn, and we can do that in terms of logs. And the basic idea, if we look at this graph, we can see that the harmonic series is actually the areas of those rectangles which are based on the curve y equals 1 over x. So the first yellow rectangle's got height 1, and then the next one's got height half because it's based on x equals 2, etc. So those rectangles have got areas 1, half, third, whatever. But we can clearly see that they are above the curve, except at the points where they just touch. So that harmonic series up to 1 over n is actually bigger than the integral, the area under the curve, which is the integral from 1 to n plus 1, and that gives you the log of n plus 1, all to base e. So in this case, the picture we've got 1 up to a fifth is greater than log 6. Now that actually is another proof of the divergence, because if the harmonic series is bigger than log n, we know that log n goes to infinity, so the harmonic series must. But Oresme wouldn't have known that because they hadn't invented logs back then, nor had they integrated to find the area under a curve. Now we can take this a step further by tweaking it. So on the left, we've got what we had before, but now we can situate the rectangles slightly differently and put them under the curve by using the right-hand end of each rectangle to generate the height. Now this time that takes us back to 0, and we've got to be a bit careful. We can't integrate 1 over x from 0 to any number because it diverges. So we need to take the block, the 1 by 1 block, and then we integrate from 1. So that gives us, for example, on the right-hand one, we've got 1 plus log 5, and that's clearly bigger than the harmonic series up to 5. So we can put that together, and we get the log of 1 plus the log of n is bigger than the harmonic series up to n, which in turn we saw on the previous slide is bigger than log n plus 1. So the harmonic series is log n plus something less than 1. And if you go into it with much more detail, for example, you could use the trapezium rule to get your idea of the area under the curve. And you find that the harmonic series tends towards log n plus a constant, and that's this constant gamma, about 0.577. It's called the Euler-Mascheroni constant, which is a lovely name. We've all heard of Euler. I suspect hardly any of you have heard of Mascheroni, but this was his claim to fame. And there are still lots of things we don't know about it, which we might come back to. And once we've got this formula, Now we can turn it round to get n in terms of h, and then that gives us that formula, n equals e. So basically subtract gamma, take exponentials, and you get n, e to the hn minus gamma. So if I want to get a total of 10, I need n to be e to the 10 minus gamma, which is about 9.5, and that gives us 13,000 terms just to get 10. But to get 100, we need e to the 100 minus gamma, e to the 99.5, which is about 10 to the power 43, which is a huge number. If you'd started counting these reciprocals at the Big Bang, 13.8 billion years ago, and you counted one reciprocal every second since, you would still be nowhere near getting to 100. I think the number of seconds since the Big Bang is something like 10 to the 18, I think, something like that. So we've hardly scratched the surface of 10 to the 43. So this thing, it grows very, very, very slowly, but it does grow forever. Let's now look at some applications of it. And the first one I want to talk about is this. This is where you're stacking things, flat objects, all equal. Could be playing cards, it could be books, it could be Jenga tiles, whatever. Anything that's flat but of the same size as each other. And we want to try and arrange them so you get as much overhang as possible. Now, if you look at the top two, you can see that the top one can have an overhang of a half because the centre of gravity of the top one is just at the pivot point of the one underneath. Just about to tip, but not quite. So that gives us an overhang of a half. Now, if you look at the top two, their centre of mass is clearly halfway between the two dots. In other words, 3/4 of the way along. So we can position the top two so that their centre of mass is just at the end of the third one down. And then that gives us an overhang there of 1/4. And after that, it gets a bit more fiddly to work out, but it's not too difficult. And you find that once you've got n of these, you can get an overhang of 1/2n. And if we add all of those up, we're getting the harmonic series once you take out a factor of a half. So you get, if you take out a half, you've got 1 plus a half plus a third down to 1/n. So here's another example. This apparently has got 46. These could be playing cards, thin items. You can see the half, quarter, sixth, eighth. So once you take out the factor of the half, you're left with 1, the harmonic series, up to 1/46. Now that itself comes to 4.4, but we're taking a half, so we get 2.2. And you can see how that's worked in this example. On the bottom left, we've got these vertical dividers, and on the bottom left, we can see that these measure the unit of 1 card. So going along to the right, we can see that the overhang is 2 and a bit units, and that's that 2.2. Now, this particular activity of stacking things to get the maximum overhang, you can cheat, and you can do some other options. And there's some quite famous ones. These are all using the idea of counterbalancing, that some blocks counterbalance the others. And you can get a much bigger overhang with proportionately fewer blocks. So this genie lamp, I'd hate to have to build it. So you've got 921 blocks and it overhangs by 10. Whereas if you did H with 921, you wouldn't be anywhere near 10. in fact, to get an overhang of 10, you need h to equal 20, and that would be a huge number. And then at the bottom, an even simpler one, we've got 20 blocks with an overhang of 2.3. So again, this is obviously much more efficient than the playing cards one, because there we had 46 blocks and we only got to 2.2. So this is already doing better, but I'm not interested in these. These are nothing to do with the Harmonic series, but they're fun. Let's look at another application. And that's the idea of trying to collect a complete set of items which are distributed randomly, and you can sort of get one at a time. So what I've got in mind, you might be a set of cards of football players, and you get a card when you open a packet of cornflakes, which is very much what I used to do as a kid. The cereal packets then always had some sort of set like this in, or a set of plastic toys, and you wanted to get the complete lot. So we assume that these are distributed randomly in the cereal packets, and we assume there's an infinite collection of them. So we're not going to change the numbers as we take one out at a time. And what we're trying to work out is how long, on average, it would take to get a set of 11 different cards. So we're going for a particular team for 11 people. Now, how long would it take me to get my first different player? Well, to start with, I haven't got any. So the first card I get will give me someone new. So that's good. But once I've got that one, the probability that the next packet I open will give me a different one is only 10/11ths, because there's 1/11th of a chance I'll get the one I've already got. So I'm opening packets now. Each time there's a chance of 10/11ths of getting a new card. And there's a basic result in probability that when you repeat an experiment with a probability P each time of a success, on average, you take 1/P experiments to get there. So like rolling a dice, you've got a 1/6 chance of getting a particular number. On average, you'll take 6 goes to get there. So the chance of 10/11ths means that on average we need 11/10ths, 1.1 packets to get a new player. And then once we've got that one, we've got 2, there's 9 left. So the chance that another packet will give a new player is only 9/11ths now. So we'd expect to do 11/9ths of a packet, and so on and so on. And eventually, once we've got 10 players, there's only a 1/11th chance of getting the final player. So actually, we'd expect to open 11 packets, 11/1. But if we add that up, we can see that once we take out the common factor of 11, we're left with a harmonic series, 1 plus a half plus a third in a sort of reverse order, up to an 11th, H11, and that takes us to about 29.9, say 30 packets to get 11 different players. But of that 30, 11 of them were just for the last guy. To get 10 different players, we probably would have taken about 19. And the penultimate term was 11/2, which is 5.5. So out of that 19, 5.5 were just to get the 10th player. So you're down to 13.5 packets, and you've already got 9 out of the 11 players. Another application of the harmonic series is what's sometimes called the worm on the elastic band problem. Here, in order to get a picture, I've pinched this slide. And the idea is we've got an ant, and it's on a 1 meter long elastic band, and it's crawling along steadily at 1 centimeter per second towards the other end. But after each second, the band is stretched by 1 meter. So after the first second, it doubles. But it doesn't double the next time. It just has 1 metre added on. Does it ever reach the end? And you think, surely not, because it goes 1 centimetre, but you're then adding on 1 metre. So surely you're forever increasing the distance ahead of it. Surprisingly, though, that's incorrect. So let's see how it's going to work. So after 1 second, the ant has gone 1/100th of the distance. And then the band is stretched. But the ant moves with the stretching, so it's still 1/100th of the distance along. It's actually done 2 centimetres now because it's 1/100th of the distance along. And then in the next second, it does 1 centimetre out of 200, so it's covered 1/200th of the band. And then in the third second, it will do another centimetre. The band is now 3 metres long, so it's done a 300th. And so you can see that the fractions it does cumulatively add up, and you can see that it's going to be our harmonic series again with a factor of 1/100th. So it's done after n seconds, it's done hn over 100, that fraction of the length of the band. Now we want to get to the other end, so this fraction has to equal 1, and that will give us hn is 100. Now that's very bad news, because we saw earlier how many reciprocals you need to get a total of 100. You need about 10 to the power 43. So for this to happen, to get to the other end of the band, it's going to take about 10 to the 43 seconds. And the band itself is being having its length expanded by 1 metre every second. So it will now be 10 to the 43 metres long. And as I said at the beginning, in terms of time, that time is far longer than the age of the universe. And this distance, 10 to the 43 metres, is far bigger than the diameter of the universe. So although in principle, the ant will get there, in practice, I'm afraid, we won't see it in our lifetime. That's a surprising result. And then another example that's interesting is the idea of records, setting records. We often hear about this nowadays. You know, I think, was it the hottest May on record we've just had, or the driest spring we've ever had? There seem to be lots of new climate records popping along. And I'll talk about that in a minute in terms of climate. But in terms of climate change, let's suppose we're living in a steady climate so that the values are just randomly distributed. Now, if I start keeping record, that's a different meaning of the word. If I start keeping note of temperatures each year, suppose I'm going for the maximum temperature in a year. In the first year, whatever I get will be a record because I haven't got anything to compare it with. So that's one record. Now, in the second year, the chance that that value is a record is a half, because it's either bigger than the first year or it's smaller. Let's suppose we're going for big. So there's half a chance it's bigger. It's just a random number. So the probability of getting a record in that year is a half. So, turning that round slightly, the average number of new records in that year is 1 times a half, which is a half. Now, in the third year, we get another value. These are random, so the probability that it is the highest is a third. Basically, imagine these 3 numbers in a line. The chance that it's the one at the right-hand end is a third, because it could be any one of them. It could be the smallest, the middle, or the biggest, and it's all random. So there's a third of a chance. So the number of new records is a third, and so on. In each year, the probability sorry, the average number of new records you get in that year is 1 over n. So after n years, the average number of records is hn. And this works surprisingly well. So a couple of places have got very good record, very long records. In Oxford, they've been doing this since 1767, and up to 2000, which is 234 years, they had got just 5 records, which you might think is really low. You know, you might have expected more, but according to this theory, H234 is 6. So it's pretty close, pretty much what you'd expect. In New York, they've been doing it from 1835 to 1994. I don't know why these figures stopped at these dates, but this is what we got. And they had 6 records in 160 years. But if you work out H160, it's 5.65. So to the nearest whole number, New York is spot on. So up until recently, climate does seem to have been behaving in a reasonably random way. I guess you could turn this around and use it almost as an indicator of climate change, that if the number of records start to exceed what the harmonic series predicts, then that suggests that it's not a random process. There's some underlying drift upwards in terms of temperature. But I'm sure there's other ways of checking for climate change. The thing about harmonic series is it's very insensitive. You've got to do lots and lots of years to get any significant difference in numbers. But when you come to other records like athletics records, that's not the same, because people are trying to do better, striving to do better. It's not just a random number. So there'd be a lot more athletic records than this would predict. So that's a few ideas about gamma and the harmonic series. Why is it called gamma? Well, it does relate very intimately to the gamma function, which is a generalization of the exclamation mark, the factorial. And I was sort of, I put an exclamation mark there as a sort of hint. The gamma function is a generalized version of the factorial, and our gamma, 0.577 ... is related to the gamma function. So it all ties together. One thing I like about this topic is it's what I might call old school maths. You do integrals, you calculate things. Modern maths is more structural, seeing whether things exist or not. And this is more doing some actual sums, which quite appeals to me. And I'd like to point to this book called Gamma by a chap called Julian Harville. And I got some of my ideas from it. It's got a lot more in it. And if this piques your interest, then do have a look at this. It's got a lot more, including some of these interesting applications. There's another one which involves finding the breaking strain of some items. Suppose you, for example, produce light bulbs and you want to see how long that they live for. And one way is to keep testing them to destruction, but you're wasting them. Using the harmonic series, in a similar way to what we've just done with records, you can get a clear idea of the lifetime in a much, much more efficient way. And there are various other problems. Another famous problem using the harmonic series is the one where you want to send some lorries across a desert, but each one can only carry a certain amount of petrol. So you send your lorries, you send some to leave some petrol a certain distance across the desert, and then the next lorry can pick up that petrol and go a bit further. And it turns out it's the harmonic series. So I could probably talk forever about this, but I won't. I'll stop now, and then you can ask any questions if I can find out how to stop the sharing. There we are. So I'll stop this and then come back to any questions live.
We hope you enjoyed tonight's talk. Remember, if you did, please do like the video, and if you're not already, do subscribe to the YouTube channel to see our latest updates. And remember, you can find all of our future events on sussexuniverse.org on our website. And please do join us for the live Q&A that's about to start now, the Zoom link in the description down below.